next week will be part 1 on derivatives. There's 2 tests on derivatives. So next week will be your first big test on derivatives, like our limit test we had. And then we'll spend 2 weeks on applications of derivatives, 2 to 2.5 weeks on applications of derivatives, and then we'll have our final test on derivatives, and then we'll be moving into integrals. And so next week's going to be finishing all the techniques of differentiation, and then it'll be 2 to 3 weeks of applications, and that does everything from physics applications to business applications to related rates, geometry applications, and engineering really is what we'll be looking at, and then we'll go on to integrals. So prove differentiability for the f of x equals the absolute value of x minus 1. So I'm checking x equals 1. So when I do that, what formula am I going to use to check for differentiability? What formula am I going to use? Alternate form of a derivative. Okay? So the alternate form of a derivative is the limit as x approaches whatever number you're trying to check. And remember, the alternate form of derivative finds the derivative at c. It figures out, does this exist? Because if this limit exists, then the derivative exists at that point. Now remember, there's four types of non-differentiability. There's corner cusp, vertical tangency, and then there's any discontinuity. Discontinuity is a little bit weird because if it's discontinuous in the original, what happens as you take the derivative? That discontinuity follows it. Okay? So if it's discontinuous in the original, it will follow it all the way through as you take the derivative. So if something has a vertical asymptote in the original, it's going to have a vertical asymptote in the derivative. If something has a hole in the original, it's going to have a hole in the derivative. If something has a jump in the original, it's probably going to be a jump, and it's probably going to add on to it. If there wasn't a hole, it's probably going to add a hole to it. Okay? And usually a jump has a hole at one part, but you might lose both parts at times. So you'll still have the jump type situation. You don't lose that just because you take a derivative. In fact, it's amplified. Okay, and I talked about that the other day. So all I got to do is check to see if this limit exists. If this limit exists, then the function is differentiable at that point. And most of you should already be saying that we know it's going to be what? What do you know about x minus 1, absolute value of x minus 1? So it's a flying V shifted right 1. Okay? So this is, we already know it has a corner at 1. I mean, that's pretty obvious. Most of you, if you know your common graphs, which we're going to review sometime here in the next week, I printed out common graphs and I added to it like your sine x over x and your 1 minus cosine x over x, your special ones that we learned. So we know this has a corner, we're just proving it. So on the AP exam, if they don't ask you to prove it, just be aware of it. Just be aware, say, hey, this is a flying V shifted right 1, so I know there's a corner at 1. And people ask me about the corner, and one of the questions that came up was, does a corner always have to have a 90-degree angle? And the answer to that is no. Okay, a corner is just simply a sharp turn. It's where you get it looks like the slopes are one thing, and all of a sudden it switches and does something else. Okay? And then when it switches with curves drastically, that's a cusp. So if you get straight lines, you get a sharp corner or a sharp turn, that's a corner. And then when you have a drastic change in the slope with curves, that's a cusp. Okay? It's not like a parabola where it's smooth. Okay? I mean, that's just gradual changing. And you expect it to do what it's expecting. Or you expect it to do what it's doing. So you're saying, oh, negative slopes going towards what? 0, and then 0 going towards positive steep. Okay, so that's different. All right? So when I look at this, it's going to be the limit as x approaches 1. Okay? The limit as x approaches 1 of f of x. What's f of x? Absolute value of x minus 1. Now, that already brings up something. Let me go ahead and stop right there. When we deal with absolute value is really what type of equation? Piecewise. So we need to understand absolute value of x minus 1 really has 2 pieces to it. We need to consider both pieces when you're doing a limit. Anytime you do limits, you have to consider twice. You're going to have to consider from the left and right. Or if you just get 0 in the denominator. If you don't get piecewise or just 0 in the denominator, then you don't have to do that. You can just do a regular 2-sided limit and see if direct substitution works. Okay? So in this situation, we're going to have x minus 1. Don't fail me now, board. It's too early. and this will be x greater than or equal to 1, and then you have negative, or the opposite of x minus 1 for x less than 1. Okay, so there's your piecewise equation. How do I know 1 is the piece where it splices? Because this is where it makes the change, because that's where it's equal to 0. 0 is the point where it changes from positive to negative, right? So anytime you want to figure out where an absolute value changes, just set the inside of the absolute value equal to 0. Okay? That has to be the point where it changes. Good morning.
Good morning.
How are you?
Morning. Morning. Just checking in.
Yeah.
Are you free first now?
Yeah, sounds
Grab
good.
you for a minute. Thanks.
So then we have x approaches 1 from the right. Okay? X approaches 1 from the right. And we'll have x minus 1 minus f of 1 over x minus 1. Okay? So, if I do this, what's f of 1? What's f of 1? 0, so we're going to have the limit as x approaches 1 from the right of x minus 1 minus 0, which is just nothing, over x minus 1. And what does that give me? Well, these cancel and you get 1, and then the limit of a constant's a constant, so you get 1. So slope from the right is 1. Okay, we're just proving it. Even though we already know it's non-differentiable there because of a corner, but we're just showing it. And if free response on the AP exam, they might have you prove differentiability. You might have to show this, and you show it with the alternate form of the derivative. I'll tell you how you can get out of that a little bit in just a second. So now I go limit as x approaches 1 from the left. Now I use this piece. This will be the opposite of x minus 1 minus f of 1 again, which is just f of 1 again is just going to be 0 again, all over. And by the way, you plug it into the piece you're actually using. You don't have to worry about where it's equal to. Okay, that was one of the mistakes I made the other day. I clarified it in both classes, but let me clarify it again. Whenever you're figuring out f of 1, okay, you plug it into the piece you're currently using. All right, over x minus 1, you're going to end up with the limit as x approaches 1 from the left of the opposite of x minus 1 over x minus 1. Those cancel, you get negative 1. And so we can clearly see, because the slope from the right doesn't equal the slope from the left, okay, this is what the derivative is approaching. So, and it's a v, we know it's one side, looks like this, shifted right 1. And we look at the derivative. When you look at the derivative, you're looking at slopes. You're not looking at points, you're looking at slopes. So the slopes are approaching negative 1, the slopes are approaching positive 1. So we see clearly that what they're approaching as x approaches 1 is not the same slope. One side's approaching negative 1, one side's approaching 1. Now here, listen, on the AP exam, you can get out of this doing the alternate form of derivative if they give you the graph. If they give you the graph, it is fair game to prove it just by looking at it and saying the slopes on this curve. So for example, let me just show you. If I had something like this, come on, move. Let's say I had here A, I don't know what it is, and let's say you had something like this, that, and you could say this is non-differentiable because of a jump, right? And that would be enough, correct? All right, so that's one example where you can say, well, it's non-differentiable because I can see there's a jump at x equals a. Another example would be if I'm talking about proving it, not just saying what it is, not just saying it's non-differentiable, but proving it. And on that last one, you'd say because of a jump, it's discontinuous there. And since it's discontinuous at that, if that was the derivative, or if that was the original function, since it's discontinuous in the original, it's going to be discontinuous in the derivative at that value. And then when you get to another one, let's see, let's do this one. And you're trying to show it's non-differentiable, here's how you prove it. Without using the alternate form of derivative, you'd just say the slope from the left is approaching what? Negative infinity. Just by looking at it, you can see that. And the slope from the right is approaching what? Positive infinity. Therefore, it is non-differentiable, and that's enough to prove it. Okay, you're not just saying it's non-differentiable because of a cosp. You're not just saying it's non-differentiable because of a jump. You're saying why. So in this one, you're saying it's non-differentiable because the slope from the left does not agree with the slope from the right. That's why it's non-differentiable. The last one with the jump, you're saying it's non-differential because if it's a jump in the original, it'll be a jump in the derivative. Now, in the weeks to come, we're actually going to learn how to sketch derivatives from the original function. So that'll start to make more sense as we do it. Okay. Let me just do one more of these. 65, maybe, and then we'll go to the other homework from last night and see if there's questions that you guys have. And then I have a couple things I want to talk about the 99th derivative of, I can't remember what it was.
It's like sine or something.
Sine or something like that. Talk about how you do that because that's coming up soon. And then we'll do some higher order derivatives. I'm going to do some things here that I haven't maybe talked about as much in class. What does 65 say?
X equals, one of them is x squared plus 1.
X squared plus 1.
And then that's x is less than or equal to 2.
Okay.
And then 4x minus 3.
4x minus 3.
And x is greater than 2.
Now, technically what you could do to prove differentiability on this is you could graph the two functions. You could graph it and splice it at 2 and just show it visually, just like I did on the last one. You could say, well, it looks like the slopes from the left are approaching this, and the slopes from the right are approaching this. But that, how many agree, graphing takes a little bit of time. You'll probably run it through the alternate form of the derivative just as fast, okay? And it's more exact anyways, okay? And your graph sometimes gets a little bit rough, and you don't necessarily know exactly what the slope. The eyeball method doesn't always work, okay? This is for sure. So I'm going to have to, since it is piecewise, I can't just do a two-sided limit. I've got to do the whole one-sided limit deal. So limit as x approaches 2 from the right. I'll do that one, then I'll go the limit as x approaches 2 from the left, and I'm going to speed this up a little bit. You don't have to write out the formula, but it's f of x minus f of 2 over x minus 2. So 2 from the right, which function am I using? Bottom one. Watch how this works. 4x minus 3 minus f of 2. What's f of 2 going to be then? Okay, 4 times 2 is 8, 8 minus 3 is 5. All over x minus 2. Still with me?
No.
Okay? Limit as x approaches 2 from the right. That's going to be 4x minus 8. Watch what happens here. It always works. Guys, these always work out really slick. Okay, what can you do? Factor out of 4. Can you already see what it's going to be? It's going to be 4. Because as you factor out 4, you're going to get x minus 2. What happens to x minus 2s? Cancel, Shazam, you get 4. The slope from the right is 4.
Do you have to do all that work? Because you can just look at the original equation.
You can, I mean, if it's not asking you specifically to prove it in multiple choice, or they're not asking you, they're just saying where is it non-differentiable, you definitely do not need to show all that work. If it does ask you to prove it, use the alternate form of the derivative. You don't have to show a ton of algebra. You could just, actually the only steps you would have to show in the AP exam, technically, is where you plugged it in and then what the limit is. They don't care how much algebra you did in your head. Okay, and if you can see it's 4, great. Okay, it's a good question. And then let's do it from the left. This one might be a little harder to see, 2 from the left, because it's probably not as obvious to see what the slope is off of a parabola. And most of you be like, well, maybe it's going to be 0. I don't think so, because at this one, if you think about x squared plus 1, that's shifted up 1. It approaches 0 at x equals 0, but we're over here at x equals 2, so it's hard for me to eyeball and know what that slope actually is approaching at that point. So here we go. So we're going to go x squared plus 1 minus f of 2. What's f of 2? 5 this time over x minus 2. Some of you probably already thinking, okay, I think I see where this is going. It's going to be x squared minus what on top? 4. So you get x squared minus 4, so then everybody's like, okay, sweet, I can do this one now. What do? Factor cancel. What's going to happen to the x minus 2's? Cancel, you'll end up with what? I'm not even going to factor it because we know what it factors into. We know it's going to end up being x plus 2. And so plug in 2, what do you get? 4. Do they agree? There you go. Slopes from the left and right do both agree, so this is what? Differentiable. One other thing you should really check for. Hold on. This is why was this problem in red?
Yeah.
I think they're trying to trick us. The slope from the left and right agree. Seems like it's differentiable. There's one more thing we got to check for. Continuity. If it's discontinuous, that's going to force it to be non-differentiable. I don't care if the slopes agree. Okay, let's review it. This is a great time to review continuity. What are the 3 requirements for continuity? Number 1, the limit has to exist. Number 2, function has to be defined, and then the limit value has to equal the what? Function value. You need to check to make sure it's continuous at x equals 2. Now, we can also check continuity for the whole thing real quick. Let's just review the whole thing. Let's see what we say about continuity for all of f of x and not just at 2. But was the directions just a check to see if it's differentiable anywhere?
Yes, it's determined whether the function is differentiable.
Okay, and the only obvious place that most of you are checking on this one is at 2, because a parabola, if a parabola was by itself, a parabola is continuous everywhere and differentiable everywhere. We don't have any corners, cuts, and vertical tangencies on a parabola, do we? No. A line, continuous everywhere, differentiable everywhere. No corners, cuts, vertical tangencies, or discontinuities. But when you put a line and a parabola together, potentially there's discontinuity. So let's check it. Let's just do it in our head. Limit, let's just say the limit as x approaches 2 of f of x. To do it piecewise, you got to check from the left to right. What is it going to be from the left? 5. What is it going to be from the right? 5. Very good. So then the two-sided limit's 5. What's f of 2? Well, 2 is defined in which piece? The first piece or second piece? First, which is 5, and we already know they both equal 5. It is continuous there. And since it is continuous there, the left and right what? They meet at the same point. Okay? And because the slopes are approaching the same thing, they're going to meet at that point at the same slopes from both sides, or however it's going to look. Okay? So this one is differentiable. It's good to go. The only thing that could have wrecked this was if it would have been a jump, like you guys said, because the slope from both sides is approaching 4. So there's no sharp turn, there's no cusp, no vertical tangency. Vertical tangency, you would have gotten positive or negative infinity for a slope. Let me say one more thing, and then let's go to your other. You can start getting your other homework out. This is not a problem. And people always ask me, what about a problem where you don't really need to check it from the left to right? How do you use the alternate form of the derivative then? If I give you f of x equals like x squared plus 1, and I ask you to check for differentiability at like c equals 2, this is not piecewise. So when you run it through the alternate form of the derivative, as long as this alternate form of a derivative exists at 2, it's differentiable. Do you have to check for the left or right on this one? No, you can just run it through the alternate form of the derivative at x equals 2 and see if it works. And if it works, the limit exists, therefore the derivative is defined there. And so it looked like this would be x squared plus 1 minus, if you put a 2 in, you're going to get 4, that'd be 5, right? Over x minus 2, and you're going to get the same situation again. You get x squared minus 4 over x minus 2. The x minus 2's cancel. You end up with x plus 2. Plug in the 2, you get 4. And that's it. You would just say it's non-differentiable. You don't need to check from the left to right. It's not piecewise. Huh? It is different. Sorry, it is differentiable. Thank you. All right, so any questions? How do you feel a lot better about differentiability now? Kind of get the idea? Okay. Main thing is, can you spot it? Okay, you got to be able to spot it because it's going to start to screw things up here as we get further into application. You're going to have to start to say, dang it, I can't even do this problem because, or I can't do it at x equals 2 because of a cusp. And that's what people who do calculus in the real world have to think about is where does the function actually work and where does it not work? And where can I apply the calculus and where can I not apply the calculus? That's what an engineer and those types of people have to think about is where are you going to run into problems. Let me push pause a second.